So good afternoon, everyone. Welcome back to Math 122. Sorry you have to be inside on such a nice day, but we'll try to make it painless. So we're going to keep talking about Chapter 4 today. So we're going to try to do 4.2 and maybe some of 4.3, depending on how fast we move. Your next homework is homework 4.1 and 4.2. It's due on Monday. Your next assessment is today. That's quiz 7. There will be another quiz next week. Is that going to be the last quiz?
Yeah, I think so.
Maybe it might be the last quiz. Okay, anyways. Office hours are unchanged, MTC unchanged, SI unchanged. Are there any administrative questions before we start in on content for today? Yeah.
The question.
Is it on 3.3 and 3.4? We can't spend any more time talking about 3.3 and 3.4 in class. But if you stay after class or if you come to office hours, then we can talk about it. What is that face for? Okay, fine. What is it? We'll go quickly.
It's a graph, so I can bring my computer up.
That question isn't on the quiz. We'll talk about it another time.
Oh, okay.
All right, so any other administrative questions before we start in on content for today? All right, it doesn't seem like there are, so let me quickly remind you what we were talking about last time. It was a super simple idea. Well, okay, I shouldn't use the word super simple idea. I should say it's got a nice visual representation. Okay, it has a nice visual representation. We want to find where is the tippy top and where is the, tippy top version of the bottom. I don't know what you would say, but we want to find the peaks and the valleys on a function, right? And what we noticed between all of these was that they all have something in common, which is that the derivative is 0 at peaks and it's 0 at valleys. And our goal was to figure out, well, I can quite easily find where are the places where the derivative is 0. But how to tell whether it's a max or a min was another story. So to figure out whether it was a max or a min, we needed to have not just that it was a critical point, we need critical point and some further criterion to classify as local min or max, right? So in order to do that, we had the first derivative test, okay, which was a simple idea which said, look, if you're going down and then you're going up, there go my glasses. If you're going down and then you're going up, right, then in between you hit a minimum, right? And if you're going up and then later you're going down, then you must have hit a maximum, right? So that was the first derivative test. So in order to do it, what we do is we find all the critical points. So let me show you what we did here. We find all the critical points first by taking the derivative and setting it equal to 0. And we know there could be a minimum, or there could be a maximum, or there could be neither of those things at critical points. So we put all the critical points on our number line. In this case, it was -2 and 8. And we know those are the places where the derivative is 0. So we know in between, the derivative will have just one sign. It'll be either negative all the way through, or it'll be positive all the way through. That's because for it to go from being positive or negative, to go from being positive to being negative, it has to go through 0, right? So that's why the derivative has a uniform sign in each subinterval. Subinterval 1 being up to -2, subinterval 2 being from -2 to 8, and subinterval 3 being from 8 onwards, right? So to check what is that sign of the first derivative, we just take any old point from each subinterval and check what is the sign of the first derivative at one point in the subinterval, and then we know what is the sign of the first derivative in the entire interval, because we know it doesn't change, except for possibly at -2 and 8. Okay, so that was the first derivative test, and if we go from being increasing to being decreasing, then we know that our function hit a maximum at -2. If we go from being decreasing to being increasing, we know our function hit a minimum at 8. Okay, so that's first derivative test. Then we had the second derivative test, which was a little bit different. So the second derivative test said, okay, let me start on on this diagram here maybe is a good place to start. And I need to make it smaller because I'm not that tall. Okay, so the second derivative test said, okay, look, if you have a minimum, you can say that it's a minimum in one of two ways. The first way is to say, well, I'm decreasing and then I'm increasing, therefore I hit a minimum. That's way number one. Way number two is to say, I'm concave up, okay? I'm concave up. So a valley always looks like something which is concave up, right? And a peak always looks like something which is concave down, okay? So it's kind of a two-part process. You have to find the critical points, and then you have to classify the critical points, where the second process is done via the first derivative test or the second derivative test. So any questions about that theory which we learned last time, which are just burning in your hearts? No burning questions? Okay, let's have some thumbs. How do we feel about critical point stuff in terms of like applying first derivative test to find minimums and maximums and second derivative test and all that stuff? Thumbs way up high so I can see them all. Thank you. Okay, that's a lot of thumbs up. I like it. All right, well, time to put your money where your mouth is because we're going to do a group exercise now. So what I want us to work on here is basically just what we were doing in class last time. Okay, we're going to try to take these two functions. Well, just start with the first one. And if you're fast and you get done with the first one, then work on the second one. So for the first one, we've just got a polynomial here. We want to find all of the critical points. So remember, critical point means f prime of x is equal to 0, right? And then how do we classify them? Once I have them, how do I classify them? Yeah?
As a min, max, or neither?
Yes, as a min, max, or neither, but what process do I use in order to classify them? You know that one too?
There's two.
Yeah, there's two, right? Name one of them. They have a name. What were the names of those tests that we had? Yeah, first derivative test or the second derivative test. Those are the names of them. But if you just know how to do it, that's fine too. All right, so get to work. I'll be coming around. Jacob will be coming around. Let us know if you want some help.
Wait, 0.
I honestly don't know what I was doing. I was doing some weird math and trying to make some binomials. I suppose you could.
You said this one's 0? The other reason that
This is going to be a lot of plugging in the equations. I should use the other one. Are you just going with like zeros?
Yeah.
I bet it does. But I still feel like that's just the easiest to remember. That's probably what I'll end up doing. Either side of these, though, you can just do like -2 and 2. Like you only need to do that.
We found the derivative, right? And now we're at minus 0. Right? So this is like a quarter polynomial, right? So in order to find minus
My
8,
phone was not meant to do this type of math.
this is first of all, something I can take out both of these guys.
You can check that.
And 15. So 15x squared, and then what do we have left? 2y. Yeah, so that's right. That's 15x squared times
As long as you got positive and negative numbers.
and then now we're going to write x squared minus 1.
I like living in my fantasy
We
land.
got something that's a zero wrong. So one of those is 0. If this one's 0, then that means that x has to be 0, right? And for the other one, we can factor that guy. You want to factor that one? It's squared. We want to factor. So we're going to leave the 15x squared. And what we want to do is just factor x squared minus 8. For, yeah, so. Two is also. No, so I think there was an issue just missing negative. Okay, so, yeah, right there, yeah, yes, it would be, but, minus 1 goes plus 1 to the other side, and your brains are going to be plus and minus. So that one difference squared factor is like x plus 1, x minus 1.
Is this all like
So yeah, 15x squared times plus 1, x minus 1.
Which one have you supposed to be done?
I'm just going in my head.
Oh god.
Yeah, negative 45.
And so now you have all these things multiplied together equals 0. You can just set each of them equals 0 to get the roots. Like go back here, you know, kind of get 0.
At my point, you said regular 4 times possible.
So those are the ones that are the number line.
I did, but like I just did it in my head. Oh wait, yeah.
Redo that math.
Literally like oh wait, I get it. I get it.
Oh shit. It might be positive.
So those are.
Wait, no.
Do you know how to type into a calculator?
Might be x.
That's a good start.
Yeah, that's right. This, I mean, I don't know. It could be, but how do you stop it? Like, what's in that?
No, it's negative. It's not.
Okay, so -1 is the max, 1 is the
Zero is the max.
it starts going down at 45. So
Wait, I thought it was positive.
I don't know. You gotta remember, I did the math in my head.
So you don't need to like what you can do now is you can rewrite this as x squared times x squared minus 1. And then
I'm getting a different
now you know
answer
what you
every
have.
row. I don't know. There's a lot of numbers that's like 0.5. Like it's not easy.
So that's the whole point, right? Is that these are where the derivative is zero, right? But in order to check whether it's a min or a max, we have to know what is the derivative doing in between. Something like -2, -1/2, -2, and then we check whether it's plus, minus, or minus, or whatever, right? You see what I mean? So now you're getting 0, right?
Yeah, I guess
That's
then we
when
only
you're
have
zero,
to-
right?
You just run it again.
Positive.
Then we get 0.
So that is not what's happening.
So to figure out,
So that 1 is the max, since it goes up
at the point
and then it keeps going down past 0 until 1.
I think one's the max.
Yeah, and then 1 is the max. 0 is or not usually. It's actually watching a movie.
Like if you're watching golf,
No, but it ain't when you play. When you see the shot, you're like, damn, I couldn't do that. This is a March Madness. I gotta watch it. On brackets and shit. I can see the judgment in my face. Just a little. Honestly, I wouldn't Yeah, too nice about bracelets. I don't, the hat is a strong
That's true. Yeah. So we found the critical points basically. You agree? Like problem says find and classify. So now we got to do step 2, which is classifying. Right? So classifying, we do first trip. Oh yeah. Okay. So which one speaks to first or second? Second one you need to use over first derivative. That's the
I'm not trying to do
hit on
that.
our number line, -1, 0. So,
I
the
don't
derivative is 0 at these
Oh, I use
What is it doing before and then after? Before and after. Before and after will tell us whether we were going up or down.
Isn't the only thing that it can be equal
What
to?
we want to do is find some test points.
Like there's nothing.
Like -2, -1/2, 1/2, and 2.
Yeah, because it just gives you
And figure and take those numbers, plug them into the first derivative, and see if we get something positive in -3 or something. It's like
Show me how to do it.
What do we do? So tricky situation here, right? You took the derivative, that looks good. And now we have this equation, e to the x equals 10, and we want to know what x is. So we get x by itself when it's inside the first, when it's in the... What? Yeah, so use the log, that's right. Yeah, logs aren't going away.
I forgot I should do that. Put the 10 to the right. Yeah. So we said it'll be
Do we need a little more time still to work? Let's have a hand. Okay, some people need a little more time, so let's take a little bit longer. Who are we finished with number 1? Let's raise our hand if we're finished with number 1, and working on number 2 now. Okay, if you're not done with number 1, don't worry. Just keep working. And if you need help, raise your hand. So, okay. Alright, so what do we found the derivative, that's done, right? And for a critical point, what does that mean? That means that the derivative is 0, right? So this is the derivative, we want to know when it's 0. So set it equal to 0. And then
to solve an equation like this? Yeah, we can take out the x squared, in fact, we can take out 15x squared, right? What would be left on the inside? X squared minus 1, you know how to factor that?
Wait a second.
Why is that?
And if 15 times x squared times that stuff is equal to 0, then you know you have three numbers being multiplied together, you get 0. One of them has to be 0, right? So the answer here is that going to be that x could be 0, that would make 15x squared 0. Or it could be that x is negative 1, make it less than 0. Or it could be that and now we have our three zeros, right? We have -1, 0, and 1, right? So here we have our critical points, and now we still have to do the second part, which is classification. Okay, so for classification, we have to do the reverse derivative test, which remember derivative 0 at this point, meaning where we created from. But we want to know what are we doing just before and just after. So maybe at like -2 and -1/2. So we want to know whether we're increasing and then decreasing, or whether we're decreasing and then increasing. You can take this -2 and this -1/2, plug them into the first derivative, and see if we can get something positive or negative. See, and if we go like negative, positive, something like that, then we're going down and up. So if you just that up? Who wants some help? What is the value of the second derivative at -1, 0? For the first derivative test, we can check what is the value of the first derivative, like to the left, and middle, second. If it's negative, it's a max limit, because negative second derivative means we are down, right? So we have to have a max. Oh yeah, of course, you can use the numbers. Go on the second one. Okay. So
You got the.
so from here, right?
All right, so for this first one, what do we do? Okay, I'm going to do two methods. I'm going to do first derivative test for the first one, and I'll do second derivative test for the second one. So for the first one, what do? We just get the derivative, f prime, is 15x to the 4 minus 15x squared, and we set that equal to 0. By factoring, I get 15x squared times x squared minus 1 equals 0, and 15x squared times x plus 1 times x minus 1 equals 0. Okay, so that's just factoring. And we have a product of three numbers, and we get 0. That means one of them has to be 0. So we just take x equals to 0. That would make 15x squared 0, or x equals -1, or x equals +1. That would make the other two 0. And then we use our number line. So for our number line, I put on -1, 0, and 1. And I know that the first derivative is 0 at each of these points. So I need to check whether we are like increasing then decreasing, or whether we're decreasing then increasing, which is done by checking the sign of the first derivative in between each spot. So I might try like -2, -0.5, 0.5, and 2. Okay, those would be good points. So f prime of -2, if I put in -2 here, what am I going to get? I'm going to get something positive times something negative times something negative is something positive, right? So I think it's positive, right? So it should go plus, and then it should be minus, and then I think it should still be minus, and then it should be plus, right? Is that correct?
Yeah.
All right. So why is it minus minus? Well, it's minus minus because x equals 0 is a double root, right? If you have a double root, your function doesn't change sign. Okay, so I kind of flew through that, but I'm assuming that you all have sort of taken these numbers, you can plug them in, you know how to plug numbers into a function, you can find out whether it's a positive or negative number. Okay, so what does that tell us? It tells us that our actual function, so maybe I'll do the actual function with a different color so that I don't get confused. So f itself, so this is f prime is positive, f prime is negative, f prime is negative, f prime is positive. What does that mean for f? That means f is increasing and then decreasing and then decreasing and then increasing. So therefore we have a max at -1, x equals -1, a min at x equals to 1, and neither at x equals to 0. Agree? All right, any questions on that first one? Also, I gotta turn on my quiz alarm. Okay, so that's the first one, and the second one, I'll use the second derivative test because it's gonna be easier. So first of all, I wanna know when is g prime of x equal to 0, so I have to find it first. It's just e to the x minus 10, set it equal to 0. And then that means that e to the x is equal to 10. And I think a lot of people got tripped up at this point because they didn't know how to figure out what x is. But remember, anytime that the unknown quantity is in the exponent, what do I have to use? Natural log. Okay, we use natural log to get it out. So ln of e to the x equals ln of 10. And what happens on the left-hand side? Just x. Okay, so at this point, if you want, you could go ahead and do a number line. But I kind of mentioned last time, there's some times where the number line first derivative test is great, and sometimes when the second derivative test might be a little faster, whatever, right? Here's a situation where I'd recommend using the second derivative test, and here is why. I find a lot of my students don't know what kind of a number ln10 is. And so they have a hard time thinking about, well, what's a number which is smaller than ln10 and larger than ln10, right? So what is ln10 really? It's probably something like, I don't know, between 2 and 3 if I had to guess, right? Sorry? So it's 2.3, okay. So, but you might not know that, so it might be hard to find numbers to the left and right. Well, the nice thing about the second derivative test is you don't have to find numbers to the left and right. You actually plug in the point itself into the second derivative. So let's go ahead and do that. So the second derivative, g double prime of x, g double prime of x would be equal to what? Just e to the x, right? And then g double prime of ln of 10 would be e to the ln of 10, which would be what? Just 10, which is what kind of number? It's positive. So the second derivative is positive. What does that tell me about g itself? G double prime positive tells me that g is what?
Concave up.
Concave up. So the function is concave up. So what do I have, a min or a max?
Min.
I have a min. So I have a local min at x equals ln of 10. And that didn't require me to have any foreknowledge about like what that number really is. You see how that sort of was a little bit easier in this case to do the second derivative test than the first derivative test. All right, so that's all I really want to say about local mins and maxes. Are there any questions about this before we close this section and move to another section? Yeah. Yeah, the second question I used the second derivative test. So that involves plugging the actual critical point into the second derivative, as opposed to the first derivative test. In the first derivative test, we're not plugging the critical points into the first derivative. We already know that that would give us 0. We're taking points which are in between the critical points. namely -2, -1/2, 1/2, and 2. Those are what we are plugging into the first derivative to see whether we're increasing or decreasing in between the critical points. Okay? Any other questions? All right, then let's move on. So next we're going to talk about section 4.2. Briefly, very briefly. And we're going to learn about inflection points. So what are inflection points? Well, inflection points are a little bit more subtle than critical points, or minimums or maximums or whatever. So inflection points have to do not with when does the function reach a minimum or maximum, which is saying something about the first derivative, but inflection points have something to do instead with the second derivative. So when the derivative, the first derivative, changes sign, that means I went from increasing to decreasing or decreasing to increasing, which means I have a minimum or a maximum. But we could also ask, what does it mean if f double prime changes sign at x naught? Well, that means that the concavity changes at x naught. So let me show you what that looks like. Okay, so let me show you what that looks like. So here's a potential function, and it could look like this. I shouldn't do it like that. I should do it like this. So it's much more subtle to identify an inflection point than it is to identify a minimum or maximum. For minimum or maximum, you just look for a peak or a valley, and you're like, hey, there it is, right? For an inflection point, it's a little trickier to see. Remember, it's where the concavity changes, okay? So I'm going to highlight two parts of this graph. The first part of this graph is concave what? Down. This is concave down. And then after that, it becomes concave up. And the point at which we change, we call the inflection point. Okay, the inflection point. I'm just trying to think about why they use the word inflection. I feel like the only thing I can think of it would be like you can have an inflection in your tone of voice, which is kind of like your register is changing from like, no, I feel like that's still, okay, forget I ever said that. In any case, we call them inflection points. It's where the concavity changes, and it's going to happen only at places, so necessary and crucially, but not sufficient condition is that the second derivative should be equal to 0. Okay? Second derivative has to be 0. But just like before, just because the second derivative is 0 doesn't necessarily mean I have an inflection point. Okay? We'll see an example of that a little bit later. All right? But that's a necessary condition. So that's where we're going to look. We're going to find all the places where the second derivative is 0, and then we're going to check whether or not the concavity changes from one side to the other. Okay? Any questions about the concept before I show you an example? All right, let's see the example then. So here I have a function, x cubed minus 9x squared minus 48x plus 52. I want to know where are the inflection points. Where are inflection points? If there are any. Okay, so I know it's when the second derivative changes sign. And I know the second derivative will only change sign at places where the second derivative is equal to 0. So those are the places where I'm going to look. So the first thing I have to do is figure out f prime of x. That's 3x squared minus 18x minus 48. And then I'm going to take the second derivative, which is 6x minus 18. And I'm going to set that equal to 0. And find that x should be equal to 3. So I found what I call a candidate for an inflection point, or a possible inflection point. And the reason I call it a candidate is I have to verify that the concavity to the left has one sign, and the concavity to the right has a different sign. And I do that using something which looks a lot like the first derivative test, but is actually going to be a test of the sign of the second derivative. So here we put 3, and we want to understand what is the concavity to the left? So maybe I could do 2. And then what is the concavity to the right? So maybe I could do 4. So f double prime of 2 is, what, we put 2 in for x, we get 12 minus 18 is negative 6, right? And if I put in 4, then I get f double prime of 4 is equal to positive 6, right? So I'm just plugging 2 and 4. I'm plugging them in for x in the second derivative, okay? Second derivative. So the second derivative goes from being negative to being positive, okay? To being positive, which means that the function itself, f of x, goes from being, well, if the second derivative is negative, that means I'm concave down, and second derivative is positive means I'm concave up. Okay, so yes, there is one inflection point at x equals to 3. Any questions on that one? Okay, maybe one way you can think about an inflection point is it's a point at which your acceleration changes from negative to positive. It's not about your speed being negative or positive. It's about whether you're stepping on the brake or whether you are stepping on the accelerator, right? It's a question of whether your speed is increasing or decreasing, right? Maybe that's one way of thinking about it. An inflection point is, of course, also a critical point for the first derivative, right? Because if the second derivative is 0, then that means the derivative of the derivative is 0, which means critical point of the derivative. All right. Any questions on that at all? No? Okay. Then let's do some group work. We're going to try to find, okay, local mins, local maxes, and inflection points for the function f of x equals x e to the minus x. And if you finish that one, then you can work on the second one, which is a question about whether or not f of x equals x to the 4 has an inflection point or not. And please justify your answer, and I'll be walking around with Jacob to help.
stays the same, right?
Yeah.
Second derivative brings it back to the first one. It's two negative positive that. So then that's the second x e to the
I got it.
What?
Okay.
Oh, wait.
So if
Okay.
you can get rid of the negative x pretty much because you could just square root that over.
So the first one's the first one, the second.
And you can't square root something that's 0, so you can basically just
You have to do product rule.
Yeah, but you already did the derivative. This is the derivative, and now you're just trying to get it to equal to 0. The derivative is the negative x e negative x.
But you also have to do the derivative of like the x times that. So it's just
Oh yeah,
one
well,
times.
you're getting the second derivative.
No, that is the first derivative.
What else can you do besides multiply?
Product rule. You have to do the product rule.
No, it has a constant being multiplied onto. You
It's
can
not
only
a
do the-
constant.
You can only do the product rule when it's a number. If you have like being multiplied by a variable.
No, I don't think that's true. It's not a constant. No, not the -1, the x. You have to take the derivative of both of them. You have to do product rule, right?
Yeah.
I told you.
Dude, I'm still like lost on where the fuck I'm going with that.
Oh, can I divide by e? Oh, wait.
Wait, so what's different about yours to mine? Well, I'm confused. What's missing?
Jack.
Okay. You have to do the product rule. So you take the derivative of x times e to the negative x, and then you do x times the derivative of e to the negative x. You
I have
know?
no idea what you just said.
So like add them.
Not like honestly, I feel like I just got a fucking flashback. So I was trying to wait, what is your derivative? Like what do you have?
I have e to the negative x plus that negative x e to the negative x. I think that's right.
On the right,
You get this
correct,
equal to 0.
but here,
I
so what we've done is you have these two functions
subtracted.
multiplied together, right? Which the product rule says the first thing you do is the derivative of the one and not the other, and then you do the derivative of the other and not the one. So that looks like f prime g plus f g prime, right?
If you
I
subtract
think what you've written
the
here is actually
over
f
and
g
divide it by the e
plus
to the
That's
negative
right.
x,
And
and
then
then
it's
it's times the negative 1.
So you get the derivative of both
Whatever
of them,
the fuck that
right?
is.
And neither of them on the
Wait.
left.
Wouldn't it just be positive 1? Or no, it would be negative.
Yeah, so I think you want 1 times e to the minus
X
x.
equals 1, right?
1.
And then
It'd be
you
negative
want-
1, I think. Because I think since both of these are. No, the x plus is negative 1.
Exactly, and then
I think
plus,
it's 1.
and now we switch the roles exactly.
If you do that, you get -1 equals negative x.
Close.
It's just
Oh, so the e to the minus
This
x,
one right quick.
right, fits into the e to the kx rule,
The
right?
only issue is I don't
So
think
we
you
had a
can do
rule
that.
which says
E to the like -2. Oh yeah, you can.
exactly k times e to the minus. So in this case, k is -1, so you could just put a minus right there.
this reading is right here, right? Next, right? 11 is -1.
Well, we also have to find all local mins and maxes, right? Local. Oh yeah, of course. You can do it by order of the two types.
Yeah.
I think so.
It's gotta be one or the other. Hopefully our problem will
Derivative of x is 1.
Oh god, there's like the derivative of that. Oh god.
Well, you can think about it in two different ways. You can think about it as the line y equals x has slope 1. You know? Or you can think about it as x to the 1 and then use the power rule. That becomes 1 times x to the 0,
Jesus.
which is 1 times 1x. Two different ways of thinking about
I
it.
got those some positive.
So now you have this, and you want to find local mins and maxes, right? Which means we want to find the critical point first. So that means take this, set it equal to 0. Yeah. So you just go to 0 here if you want.
Stays. No, wait, no.
What's up, you?
No, it turns into. That's a different rule, isn't it? I'm gonna go back in time.
So, what is x times minus
No
1?
way.
X is minus x.
Right.
And negative x plus 1 is the same as 1 minus x. So this is just e to the minus x times 1 minus x. Yeah, of course, yeah. It's multiple, or it's like a greatest common factor, right? So, at this point, right, what do you have? You have two things being multiplied together equals to 0. And then one of those two things has to be 0, right? So, well, in factoring, we set them both equal to 0, because it could be that either of them could be 0 for different x values. But it turns out that e to the minus x is never 0. You know why? Well, we can see it in the following way. We can look at the graph. What is the graph of e to the minus x? Exponential decay
-2
going
e to
down.
the negative x
Like
plus
so.
x e to the negative x.
So, if you ask, well, when is e to the minus x 0? For what x value? It's never 0. It keeps getting closer and closer and closer to 0, but it never touches 0. That's a graphical representation. The other way you could do it is by solving. You take e to the minus x equals 0. Natural log on both sides. You get minus x equals 2 ln of 0. And ln of 0 is undefined. If you plug it in on your calculator, you get an error. So this is never 0. So we have a number which is never 0 times another number is equal to 0. Then the second number has to be 0, right? So in that case, we just solve this equation, which you have here, minus x plus 1 equals 0.
I don't even know what it is. Like I was doing it wrong, and then I got yelled at by her and
I did not.
about how I'm
But
stupid.
e to the x part.
And I don't know what the fuck's happening.
But otherwise, it's
I'm trying to understand, but I just don't.
Product properties is I have two things, put them together, I get 0. One of
I
them.
got no inflection point. There's just no way that that's
There's a
right.
little bit of reasoning. The fact that e to the minus x would never carry.
So I just
This one is pretty cool. Never carry. Zero. Yes, 0 when x is 1. Right? So that's the critical point. X equals 1. And there's just only one critical point.
I don't think there is an inflection point.
And then you gotta classify whether it's a min or max or neither.
Isn't the inflection point just -1? That's when it changes directions. Like, or no, it's not. That's not changing cavity. So there is no. It's just up and down.
It just looks like the graph like that, and it looks like that.
Yeah, but this one
It's just like-
So something positive and something negative.
If it goes like, it's like that.
Yeah, something positive.
Is that like considered an inflection? Because it's going above the line with this is like an inflection.
No, it's not changing in gravity. Like it's
No, but if See, it like goes above it and then it comes down. It's like still a small like. That's still.
We can't get that now.
I don't know.
Okay, let's talk about it as a group.
Yeah, please talk about.
Okay,
it.
I'm sensing some confusion.
My entire life is a lie.
Who feels confused by number 1? Okay, that wasn't my intention, but let's work through it together. So what the hell is going on with number 1? Well, to find local mins and maxes, I got to find the critical points, and then I have to classify them using first derivative test or second derivative test. So let's do that. So f prime of x by the product rule is equal to 1 times e to the minus x plus, actually minus, x times e to the minus x. Okay, so that's from product rule, these two things being multiplied, and linear function rule and e to the kx rule. So those are the rules, and we want to take this and set it equal to 0 and ask ourselves, when is this going to happen? So, when is that going to happen? Well, we can factor out an e to the minus x, and we leave 1 minus x, and we say this is equal to 0. And just like in every factoring problem that you've ever done, if you have two things and you multiply them together and you get 0, then one of them had to be 0. Yes? And here's where I think a lot of people ran into trouble. You think, well, we just take each of them and set them equal to 0, right? 1 minus x equals 0. Well, this one's easy. We just get x equals 1. What about this equation? Well, this equation, it turns out it doesn't have any solutions. And you can see this in two ways. You can see it graphically, which is, what does the e to the x function look like? It has an asymptote at 0. So its height is never going to be equal to 0, because it just gets closer and closer but never touches. The reason that that happens is because, look, as x gets really large, okay, 1 e to the minus x is just 1 over e to the x, which when x is really big, it's true this denominator will be huge, but never large enough to make a fraction with 1 on top to be 0. Okay, this fraction will never be 0. All right, so we can forget about this one. It doesn't give us any solutions. So our only critical point is x equals to 1. So we could use the first derivative test to put 1 on the number line. And I'm going to choose two test points, maybe 0 and 2. And I'm going to plug them into the first derivative. F prime of 0 would be e to the 0 times 1 minus 0, which is a positive number. F prime of 2 would be e to the 0 times 1 minus 2, which is a negative number. So we go positive and negative, so our function f is increasing and then decreasing. Yeah.
How do you know the second one's 0? Because like e to the 2 is.
Oh yeah, sorry. What am I doing? So yeah, 0, and this should be e to the this should be e to the minus 2. But e to the minus 2, we said, is always positive. E to anything is always positive. So this is a positive number multiplied with a negative number gives us a negative. Yeah?
Why did you change x e raised to the negative x to just 1?
So what I actually did from this step to this step is I noticed that I have a difference here, right? Something minus something else. And both of them have e to the minus x as a factor, yeah? So I took the e to the minus x out of each of them. This is e to the minus x times 1. And the second part is e to the minus x times minus x. Okay? All right, so we have a local max at x equals to 0. And we still have to determine whether this function has an inflection point or not. So to do that, we need the second derivative. So what's the second derivative? The second derivative, f double prime, will be minus e to the minus x minus, and in these parentheses, we need to write down what is the derivative of x e to the minus x, which is what we did before, right? So it's going to be e to the minus x minus x e to the minus x. Yeah. So combining these, we get, well, I guess one way to write it would be to write it as x minus 2 times e to the minus x, which is equal to 0 if x equals 2. So to determine whether x equals 2 is an inflection point or not, we put on 2, and we mark down maybe 1 and 3, and we check f double prime of 1. If we did 1 in here, we would get something negative. And if we did f double prime of 3, positive times positive is a positive. So f double prime goes from negative to positive, therefore the function f itself goes from concave down to concave up. So yes, x equals 2 is an inflection point. Okay. Final questions before we take the quiz? All right, if not, then please clear your desks. If you have a hat, please put it backwards. If you have an Apple Watch anywhere or some other kind of smart device, then please put it away in your book bag as well as your cell phone.